topic for today's session is two-port networks. This is a diagrammatic representation of a two-port network. You might be familiar with the term network. A network is a system that consists of a set of interconnected circuits for performing specific functions. A circuit or a combination of interconnected circuits that is designed for a particular function can be termed as a network. And a port is a pair of terminals at which a signal may enter or leave the network. Usually, we say like a point at which a signal may enter. But a port specifically defines the pair of terminals through which a signal may enter or leave. Here, I have termed two pair of terminals, one 1' and two 2'. One 1' represents the input port. Here we can see a few terms in this side, that is I1 and V1. I1 is the current that flows through the input port and V1 is the voltage that is experienced across the input terminals. Similarly, we can define the output port, which is here marked as 2'. Here also we can find two terms, namely I2 and V2. The current through second port as I2 and the voltage across these terminals as V2. In a two-port network, we can define different parameters. Mainly, we can categorize these different parameters as impedance parameters or Z parameters, admittance parameters or Y parameters, H parameters, and ABCD parameters. Let's move on to the first category, Z parameter. It can even be termed as open circuit impedance parameters. The term Z is familiar to us, it's impedance. If there are only resistive terms, we can simply say as resistance. But if there are components like capacitors and inductors, we need to use the term impedance instead of resistance. We know the relation explained by Ohm's law. V is equal to IR. As we are dealing with impedance, I have written it as V is equal to Z into I. This is a matrix format representation of Ohm's law when applied to a two-port network. I repeat, V is equal to Z into I. For a two-port network, V is not a single term, but it is V1 and V2. And similarly, other than using a simple term for I, we are using I1 and I2. In matrix representation, we need to do a detailing of the Z position as Z11, Z12, Z21 and Z22. We can even represent this as equations. V1 is equal to Z11 into I1 plus Z12 into I2. And the second equation, V2 is equal to Z21 into I1 plus Z22 into I2. Let's discuss these equations in detail. V1 is equal to Z11 into I1 plus Z12 into I2 and V2 is equal to Z21 into I1 plus Z22 into I2. I think you remember the other term used for a Z parameter, open circuit impedance parameter. Now, it might be clear why we use this term. It's simply because we are evaluating the Z parameters by open circuiting the circuit. Let's discuss how to evaluate the values of Z parameters. It's a two-step procedure. First one, open circuiting the input port, and second one, open circuiting the output port. We can do this one by one. We'll start with the step open circuiting the output port. Keep one thing in mind. If a terminal is open circuited, there is no path for the current. As we have open circuited the output port, the current I2 will not find any complete path to flow through. Thus, I2 becomes 0. By considering this point, it is obvious that there occurs some changes for these equations. Looking at the first equation, I2 is equal to 0 means this term becomes 0. So the remaining equation is V1 is equal to Z11 into I1. We can find the value of Z11 as Z11 is equal to V1 divided by I1. Similarly, we can substitute the value 0 for I2 in second equation. Then the equation becomes V2 is equal to Z21 into I1. Z21 can be found as Z21 is equal to V2 by I1. These are the two equations that we obtain by setting I2 is equal to 0. Z11 is equal to V1 by I1 when I2 is equal to 0 and Z21 is equal to V2 by I1 when I2 is equal to 0. Let's move on to the second case. I1 is equal to 0. That is, input port is open circuited. Applying the value of I1 in first equation, we get V1 is equal to Z12 into I2. That means Z12 is equal to V1 divided by I2. Similarly, the second equation also gets changed. The first term is inactive and the rest is V2 is equal to Z22 into I2. That is, Z22 is equal to V2 divided by I2. I repeat the equations. Z12 is equal to V1 by I2 when I1 is equal to 0. Z22 is equal to V2 by I2 when I1 is equal to 0. Each parameter has got its own name. Z11 occurs in the input port and it is called input impedance. And that too, it is obtained by open circuiting the circuit. So, it is called open circuit input impedance. Next term, Z22. This deals with the output port and it can be termed as open circuit output impedance. Next term, Z12. Z12. 1 represents input and 2 represents output. Here, both the terminals are involved. So, it can be termed as transfer. As there is a transfer from input to output, it is termed as reverse transfer. So, it is called the open circuit reverse transfer impedance. And the last one, Z21. This is also a transfer impedance and its direction can be termed as forward because it is from output to input. So we can call it as open circuit forward transfer impedance. We can even directly define the values of Z parameter from its name. Consider Z11. Z denotes impedance, so it will be V by I. And Z11 indicates that numerator and denominator can be denoted as V1 and I1 respectively. The next one, Z12. Here also the relation will be same and Z12 can be written as V1 divided by I2. Moving on to the next one, Z21 V2 by I1 and Z22 V2 by I2. Thus, we can define it easily. Now, we are going to solve a problem so that you'll find it easy to get Z values from a circuit. The question is to find the Z parameters for the network. We now know the procedure for obtaining Z values. In a step-by-step manner, we need to open circuit the input and output ports. We are now moving on to the first step, open circuiting the input port. In this diagram, this will be the input port. We need to open circuit this position. When open circuiting, the current I1 loses its path, that is, there won't be any current flow through this 5 kilo ohm resistor. So, we can redraw the circuit without this 5 kilo ohm resistor. Now, our circuit has been reduced. We have already discussed the two Z values that we obtained during this stages, Z12 and Z22. We'll first pick the relation Z22 is equal to V2 by I2. Here, V2 and I2 are unknown terms, but still we can get the Z22 value. I'll explain it to you in detail. What we have to do is, we need to make both the numerator and the denominator of similar terms. For example, here we have V2 in the numerator. Somehow, if we are able to express V2 in terms of I2, then the numerator and the denominator will contain similar terms. Then it will be easy for us to simplify. The choice is yours whether to change the denominator or the numerator. I have chosen to change V2. V2 is seen here in this position. Are we able to write V2 in terms of I2? While observing this circuit, we can find a closed loop here. Then we'll go for Kirchhoff's voltage law equation. We are familiar with the Kvl equation. The algebraic sum of voltages in a closed loop will be equal to 0. Here, V2 acts as a voltage source and a voltage drop occurs across each resistor. Kvl equation will be like total voltage is equal to sum of voltage drops. The voltage drop across first resistor can be expressed as V is equal to IR, that is I2 into 3K. Let's try to complete the Kvl equation. V2 is equal to I2 into 3K plus, moving on to the next resistor, 12K into I2. Same I2 is flowing through the 12 kilo ohm resistor because it is in series connection. V2 is equal to I2 into 12K plus 3K. I have taken out I2 as it is common to both the terms. We have obtained the V2 value in terms of I2. Now, what we have to do is to substitute this into the first equation. Equation has become simple because the numerator and denominator are having similar terms. They will cancel out and the remaining will be 15 kilo ohm. Don't forget to put the unit of impedance ohm in the answer. By open circuiting the input port, we got only one parameter, that is Z22. One more is left, Z12. Here also the numerator and the denominator are the similar terms. Let's try to change the value of V1. V1 is seen here, or it can be considered as the potential across 12 kilo ohm resistor. The potential drop can be calculated using the Ohm's law. V is equal to I into R. Current through 12 kilo ohm resistor is I2. Then V1 is equal to I2 into 12K. Thus we have obtained our desired effect, that is V1 is now represented in terms of I2. Z12 can be written as V1 by I2, that is I2 into 12K divided by I2. The I2 term will get cancelled up and the answer will be 12 kilo ohm. Moving on to the next case, that is open circuiting the output port. This portion should be considered as open circuited. That means current flow through 3 kilo ohm won't occur. So we can redraw the circuit. The parameters that we get from this case are Z11 and Z21. Let's consider the first case. Z11 is equal to V1 by I1. We are repeating the same steps as before. We are trying to change the V1 term. Considering this as a closed loop, we can apply KVL. V1 acts as a supply voltage and voltage drop occurs across the two resistors. V1 is equal to 5K into I1 plus 12K into I1. This can be simplified as I1 into 17K. This can be substituted in the above equation. Z11 is equal to V1 by I1. That is equal to 17 kilo ohm. I think now you are thorough with the steps. One more parameter need to be found out, Z21. V2 is the voltage experienced across the 12 kilo ohm resistor. By Ohm's law, V2 is equal to I1 into 12K. We can substitute this value. Z21 will become I1 into 12K divided by I1 and we will obtain it as 12 kilo ohm. Now we have come up with the final answer. Z11 is equal to 17K, Z12 is equal to 12K, Z21 is equal to 12K and Z22 is equal to 15K. Same question can be solved using a simple method. The only criteria is that the network should be a T-shaped network. A T-shaped network. We need not have to do all those steps. It's very simple. I'll explain it to you. The network shown consists of two closed loops. We'll first apply KVL to the first loop, that is to ABEF. Here V1 acts as a voltage source and drop occurs at 5 kilo ohm and 12 kilo ohm. Drop across 5 kilo ohm can be written as 5K into I1 and that across 12K can be written as 12K into the effect of two currents should be considered here, that is 12K into I1 plus I2. Then the equation becomes V1 is equal to 5K into I1 plus 12K into I1 plus I2. Expanding those within the brackets, we get 5K into I1 plus 12K into I1 plus 12K into I2. I2 terms made simplified. V1 is equal to 17K I1 plus 12K I2. Note down this as our first equation. Similarly, applying KVL at B, C, D, E. We'll solve in the direction of the current I2. Here, V2 is the source and there are two voltage drops. The KVL equation will be V2 is equal to 3K into I2 plus 12K into I1 plus I2. We can simplify this in a similar manner. V2 is equal to 3k I2 plus 12k I1 plus 12k I2, and it gets simplified as V2 is equal to 12k I1 plus 15k I2. This will be our second equation. Let's closely observe these two equations. We are going to compare these with the standard set parameter equations. We can see that these equations keep a same format. 17 kilo ohm is seen in the position of Z11. Similarly, 12k for Z12, 12k for Z21 and 15k for Z22. We have got the same answer as before, and that too in a simple way. Keep one thing in your mind, this method is applicable only in the case of a T-shaped network. Thank you for watching.